a crystal field splitting diagram. And this is for an octahedral case. And the diagrams are going to look different depending on what the geometry is. So when we draw this diagram, energy is going up. And we're going to start with our 5 d orbitals. And so this is going to be the average energy. The average energy of our d orbitals. And so this is then with a spherical crystal field. So that's where the ligands are distributed around uniformly. So it's all spherical. They aren't set up in the octahedral case yet. Our octahedral diagram is going to be over here. But this is the case that this represents. If you have all your ligands spherically distributed around your metal, then the energy of all the d orbitals are identical, because every d orbital has the same amount of ligands. It's uniform. It's symmetrical all around the metal. And I just want to tell you that this was very exciting to me when I saw this. I've been teaching this class for a while, and I never had a real spherical crystal field around my metal before. And then I walked into Walgreens one day, and I was very excited to see that Walgreens sold spherical crystal fields. I mean, you never know what you're going to get. I'm a big fan of Walgreens. I found a lot of good stuff, you know, toys for my dog, et cetera. But this was really amazing. So I asked the cashier on the way out, you know, whether they knew they were selling spherical crystal fields. And they did not, actually. So you just never know what you're going to get. OK. So in that case, where the ligands are uniform all around, the energy is the same. But now, if we have an octahedral crystal field over here, so we have our octahedral crystal field. Then we get some splitting. So some of our orbitals are going to be destabilized, and they'll be higher in energy here. So we have the dx squared minus y squared and dz squared over here are going to be higher in energy. And we're going to have 3 that are lower in energy. So we'll have our dxy, our dyz, and our dxz over here. Will be lower in energy. This difference is called the octahedral field splitting energy, because it's the amount of energy that the octahedral field is split. So over here, we can put, this is for the octahedral case, crystal field splitting energy. And again, some of the orbitals go up in energy, some of the orbitals go down in energy, and the overall energy needs to be conserved. So if 2 orbitals go up in energy, and 3 go down in energy, then to have everything add up, you can say that 3 go up in energy by 3/5, and these 3 orbitals are going to go down by 2/5. So overall, the energy of the system is maintained. OK, so that's a crystal field splitting diagram for an octahedral case. And now let's look at some examples of this. So let's look at an example. And we're going to have a chromium system that has 3 NH3 ligands and 3 Br ligands. Now you tell me what the